Ja, gut, das gehört zur Kategorie. Hab ich ja gemerkt.
Genau, überwiegend hier für die Demos klicken wir dann jeweils. Here, you should come to our evening event, 7 to 9. It's one U-Bahn stop from here. We'll have drinks and food and a couple of talks.
Everybody who has a
somewhere, I don't know.
seat next to him free, raise your hands please. And if it's your girlfriend that's not coming yet, skip her.
We can always cheat in all parts, right? We'll just say, okay, well, then we have to extract this here. Practice, good night.
Yeah, they already know about us.
Oh, it's your own.
Oh, so we fixed it somewhere.
I have to, I'm in 640 by. It's fine.
Yeah.
You know, here I have like 5 of them. I have to shorten my cell phone. But it works, yeah, I'm good with it.
Well, it's better readable now.
Yeah.
Ask them if they can plug in.
But if it's too much work, it's okay. We can do it like that.
Yeah. We'll need to switch a couple of times between the projectors, and in fact, the other one is the one we want to start from. But I think that they know this. It just went up.
Check.
Right.
We did the beamer guys not ready yet.
Okay. Where they count the money.
We need
Yeah.
this.
Oh no, this is where they count the money. Yeah.
No HDMI. No. They don't have here.
They definitely have good seats.
We have it already. The beamer is working now. It's okay like that.
Okay, you ready?
We solved it.
Go for it.
It wasn't perfect.
Is this okay for you?
It's okay.
Okay, don't bother. We take this.
Hallo.
Wir machen nichts live. Es geht einfach nicht, ne? Ja, habe ich. Ja. Wahrscheinlich genau für die 4 Tage abgeschaltet, ja.
Das ist selber kompliziert. Macht's ja noch.
Ist es auch?
Aber gerade reinsprechen bitte. Nano und sprich dich Nano.
Yeah. So, hi everyone. I'm part of the Hexen and we want to announce something. Loud, nearer? Better? You got a scream in there. Okay, so I'm going to be really loud here. I want to do an announcement. Tomorrow morning there is the Hexen breakfast. I'm sorry, women only. In the last years we had some locals around, so we decided to make it only women only. But when you have time after 11, we have some talks and they are open for everyone. We are down in the basement in room A03. And I think 11, it's my talk about bioinformatics and machine learning introduction. And I brought some current research for 1 hour. The second talk is made by Silly.
I will give a talk about sentiment analysis. I'm working in that field. I'll give an introduction to the field. I will present some basic techniques, but also some bleeding edge research that I'm working on at the moment. And if there is time left, I will also give a talk about games with a purpose. So there are some tasks where you need a lot of training data, and you don't want to create that manually, so it's time-consuming and expensive. So there are some smart people, they build games, and people playing that games, they produce a large amount of annotated data, and it's really fun playing those games.
And we have a third topic. We will get to see a part of a documentation about female hackers. We are not quite sure, but we are fascinated figuring out what this will be about. We will be finished with our program around 2 p.m. And so if you're around, we would be happy to see you between 11 and 2. Or if you're female, you can come around 10 and get some coffee. See you tomorrow morning.
Should we start?
I guess that's
Yeah, but we're 5 minutes over, but yeah, it gives us 5 minutes more. I mean, it's full. It's not going to get any fuller, huh? Is it?
Are there any open seats left? I don't. Wait, what? That right there? Oh, it's free. We have one free seat in the third row. Would anybody like it? One free seat in the third row. Do we have a taker? We have a taker. All right. Any other free seats as we attempt to do room optimization? Oh, okay. We've got 3 seats. Oh, no, keep your hands raised. We have free seats for those of you coming into the room. Door B, do we still have a queue? Any queue? No, it's not here, on this side. Huh? Oh, we've already optimized it? All right, sir, give them a round of applause. They've already got it going. Yeah, just so you guys know, based on feedback from yesterday, we're working on the procedure. We thank you for your cooperation, helping us get as many people into the big popular talks as possible. Give yourselves a round of applause for being great and very cooperative and very awesome. Thank you so much. You guys sound a little bit tired. And how many people got a full 8 hours of sleep last night? Okay, so how many people got closer to like 6 or 7? 5 or 6? 4 to 5? 3? Okay, all right, so 4 to 5, 2, 1. How many people didn't sleep last night? Wow, that's actually pretty good for day one. That's not bad. All right. The standard announcements apply. Don't forget to drink more water, use the bandwidth, that sort of thing. Am I forgetting one? I always think like I'm forgetting one. Am I forgetting one? Don't drop the what? Don't block the aisles. Yes, that's also very important. So you, sir, who is sitting in the stairwell right there in front of the escape, we're going to have to kind of move over just a little tiny. Yeah, that's good. That's good. But yes, we're going to try to get as many people into the talk as quickly as possible. Right now, once the room is full, once all of you guys have no free seats available, one seat available right there. First row? Oh, wow. Would any of you guys back there like a front row seat? I think we've got have we got a race condition going on here? Uh-oh. That guy seems to have something around his neck. You're both going for it from... Oh, no, that guy's leaving. Phew. I hate it when that happens, when I announce, oh, we have one free open seat. You know, the best possible scenario is if one person goes to get it. Second possible scenario is if nobody wants it. But the worst thing is when 3 people just rush from all different sides of the stall to try to get that one free seat. So you've got 2 unhappy people who are going to be asked to move out of the aisleway at that point. But yes, the procedure for the room for the rest of the day is when we are totally full, when there are no more seats, You should queue up behind door C or door D, those two doors in the back there, so that we don't interrupt the speaker, so that we can create as minimal disruption as possible. If your friends didn't quite make it in the talk, the Cert Angels are going to try to do their very, very best to get all of those people into all the little tiny crevices of the room. But so far this year, I think we've been a little less crowded. Have you guys felt a little less crowded this year than last year? How many people were here last year? Okay, now of the people who are, no, keep your hands up. Of the people who were here last year, put your hands down if you think we're more crowded this year. Put your hands down if you think we're more crowded this year. Okay, so it's split. It's about half and half, 50-50. Yeah, go ahead, round of applause. So we're going to try to get as many people in. So there are still spaces in the back. If we have a situation where we're very, very, very crowded, right now you see all of the guys who are in the back there. Do you guys have enough space? Do you have space to stretch out a little bit? You're good? Give me a thumbs up if you're good back there. Wow, that's pretty good. But if we ever get into a situation where we're really, really full, everybody in the back is going to have to stand for two reasons. One being just to allow more people to get into the room as possible, and also, right now those guys are sitting down, they have space, so in the event of an emergency, they can get up and they can leave very quickly. But if we have many, many people sitting back there, it can create a problem. So if we have to get as many people in as possible, we'll ask you to stand. That might be a possibility, and they're loading in people right now. We've got 1 minute left to go. Karsten, we didn't have a chance to talk. I didn't have a chance to introduce you. You always have the popular talks. It's always with you and the GSM. You're kind of, it's like Karsten GSM. It's like Dan Kaminsky and DNS. I don't know what's going on. So everybody give Karsten a huge round of applause. Take it away.
Good afternoon. It's great to be back to again be talking about GSM. I want to take a somewhat wider focus this time, talk about related areas of GSM that since last year may have popped up as the new security features or suspected security features, and hopefully throughout the hour clear out all these suspicions that there may be security left in GSM. I'm delighted to be here with Sylvain Monod, programmer from Belgium and a mastermind when it comes to GSM protocols. Planning a couple of demos. Hopefully they'll work out, certainly well tested. So by the end of this, you will have seen a live GSM hack end-to-end, hopefully putting to rest the discussion over how secure these networks are and starting the discussion of how to secure them better. Taking a wider focus, as I was saying, on what makes these phones secure or what was supposed to make them more secure. However, we're not going to look at every single part of the GSM ecosystem. The research interest, fortunately, in GSM is increasing so fast that other people are looking at all the remaining parts of this ecosystem already. They're looking at the little computer phones we have now and how they're exploitable through malware. They're looking at the air interface, which is our primary focus of our research and of this talk. They're looking further into the networks, though, where the data that's being sent from the phone to the base station now propagates through an operator's network, perhaps through several operators' networks if your phone is roaming, and they're looking at data stored in backend systems. So all of this is a 20-year-old infrastructure. It's lots of private data and with little security. We'll be focusing on the one part of this security chain that's most exposed, the air interface, the data that's being exchanged between a phone and a base station. And hopefully get the idea across that on this air interface, much too little protection is provided for us to use it to transmit critical data. This is very much a follow-up to last year's talk and to last year's research, where the focus was much more narrow on cryptographic problems. And the GSMA, the umbrella organization of all the GSM providers in the world, rightfully remarked that looking at just cryptographic problems is not going to lead to a real hack of the system. No, it will never constitute an actual threat to call privacy. So they put towards us a challenge of please also identify your target and capture the data of your target before you apply your cryptographic insights of cracking keys and all that. So those missing pieces we want to deliver now to you, and a lot of this has already been released as open source software. The rest of it is some simple scripts that you as a researcher should be able to create yourselves, but that we won't release for the abuse potential, of course. What we want to demonstrate over the course of a couple of demos and the next hour is a scenario that works as follows. You become aware of somebody's phone number, just a phone number, nothing more, and you want to find where they are in the world, and you want to listen to all their calls and read all their text messages. And that's possible with cheap, very cheap, I should say, hardware and some open source software today. Let's get started. Three phases of the attack. First, find your target. Second, capture the data that target exchanges with the network. Finally, process that data to crack cryptographic keys and derive voice data from it again. Each of them will provide some theoretical background to make you appreciate the complexity, the number of steps needed to actually get this working, and then hopefully demonstrate each of them. So, locating a phone anywhere in the world. You'd think that's hard, but that actually, to some level of granularity, is the easiest part of this exercise. Due to the way GSM operators cooperate amongst each other. There's a global fabric, the SS7 network, that interconnects all the GSM providers that allow each other's users to roam in each other's network. So they need to be able to exchange information. As a side remark, all of this has been presented at this conference already a couple of years ago by Tobias Engel. So this is just a summary again, so you understand how all the different pieces are fitting together. So over this global network that the GSM operators use to coordinate, messages are exchanged such as, where's your subscriber currently? When I send Sylvain a text message, my operator will ask in Belgium where his phone is, and get as a response, he's currently in Germany, so send your text message to that location in Germany, it will then deliver it to his phone. So it's a tracking service that's required for SMS delivery, at least how it was architected back in the day and still used in most networks. We can, of course, abuse this capability to track down people. Operators themselves can go much further than this so-called HLR query that's exposed on the internet, and even ask for what cell somebody is currently connected to. So while I'm getting the information that Sylvain's phone currently is in Berlin, but not in Hamburg, say, an actual GSM operator would get the information he is connected to the cell Alexanderplatz, Berlin, Germany right now. So much finer granularity. And any GSM operator can do this. We'll leave it at the LiDAR capability though, since that is exposed on the internet through providers that sell the service for marketing for So the scenario goes as follows. You start off with somebody's phone number, you look it up through one of these HLR services. It tells you where to send your text message to if you want to reach that person, right? That gives you a city, or at least in rural areas, a rough location of that person. You want to increase that granularity by driving around that city and finding out which location area the person currently resides in. Location area is the next level down in granularity. Berlin will have a couple of location areas for each of the operators. So for each of the location areas, you start listening to traffic announcements in that location area, and you send text messages to the phone. You will either see text message being delivered as you send them or not. Gives you an indication of whether you are currently in the right location area or not. These text messages don't necessarily have to show on the target phone either. There's the nice function of silent text messages that do get delivered over the air interface, but never show on the phone. Where operators block silent text messages, you can send broken text messages. So text messages that the phone doesn't really understand. It's being delivered to the phone, and the phone will throw it away since it doesn't understand the type or anything about the text message, right? Using this technique, you find where in a city somebody is. Last level of granularity, of course, is the cell itself. Driving around the dozen or so cells within a location area, again, using this SMS trick, you find what cell somebody is connected to, right? And that's the first thing we want to demonstrate. Can we switch to the other projector, or to the other computer for projection, please?
Okay. So I'm targeting this phone. I know it's, well, here. So I know its location area just because there is here we only receive one. So there is just no question. I'm going to use one of these phones to listen to every mobile that gets paged. So I'm just starting. Okay. Starting the phone. Okay. And then I have some Python script that basically sends SMS automatically, looks who gets paged, and try to correlate the various events on the network to find out where my target is. So here the two arguments are the phone number and the IMSI that I got from a HLR query, and these are some parameters that are transmitted and clear on the network, so I just grabbed them beforehand.
So basically, every phone is notified in the entire location area when a text message is about to be delivered to it. And then the phone is requested to announce that it's still there in the location area. And then the actual delivery will take place. We're only listening to the announcements ahead of time.
Okay, so but here it just collects some data to see who gets paged, even when I don't send an SMS, then I will send an SMS and try to correlate the various events. You just have to, it's all automatic from here, you just have to wait.
Mm-hmm. So we're solving an equation here with several unknowns. Not only do we not know where the phone is, which we're trying to find out, we also don't know the temporary identifier of this phone. The network will assign a new identifier to the phone every day or so. With this technique, we find both at the same time, though. By sending several text messages with a defined spacing, this pattern will show up as this identity receiving something from the network every 30 seconds or whichever we set. And then we know, yes, it's here, and also what TIMSI, the temporary identifier it uses currently.
Yeah. So it sent the first SMS, and it got the delivery report from the network, so I know that the mobile was paged. And here you can see that there are two mobile that were paged that match my potential target, so I'm just waiting a little, and then I'll just do the same again, and hopefully there will be only one that was in both of them.
Mm-hmm. So the entropy of this, of course, diminishes as fewer phones are online on the cell. The more activity, the longer the search, since some other phone may show up as exactly receiving a paging in the spacing you set.
Okay, so it found a single match, and it says, okay, the TIMZ is 616B1A4C. And,
Let's verify that, yeah. So this phone has a nice monitoring mode where you can query it for all this data. 616B1, yeah.
A4C.
So now we know the phone is actually here, and we know it's TIMZ. So next steps. Can we switch back, please? Thank you. Now we want to grab data off the air interface that would allow us to crack the key, but then read that data given the key, right? Again, a little bit of background so you understand what's going on here. GSM phone calls use numerous different frequencies or channels to execute different phases of a call. Basically, a GSM call works as follows. The phone is listening to what's called the beacon channel, where all these announcements are happening, the pagings we just listened to. These were on the beacon channel. The base station, when say it wants to announce to the phone that it's being called and connect through the call, will ask the phone, "Are you still here? Please respond to this paging." And if the phone does respond, the base station will immediately say, "Okay, let's continue this discussion on a different channel to keep this beacon channel as free as possible." This could be a different time slot on the same frequency. This could be a different frequency. This could even be a set of frequencies among which the phone hops. The base station determines all of this, and it much depends on the operator configuration and their sense of noise resistance, mostly what configuration they are choosing. So on this control channel, the phone is now typically asked to start encryption with a key that's already negotiated between the base station and the phone. If no key is negotiated yet, it will happen now too on this control channel. So in any event, they switch on encryption, and only then the base station tells the phone what's going on, that it does receive a text message or that it does receive a phone call right now. Now, after basically sharing this information, the channel is changed again to also keep free this control channel that's used for different phones' control information. And now, typically, the base station will ask the phone to start hopping among various channels to increase the noise resistance, so that if on one channel there's a lot of noise, some data of the other channels still gets through to the phone. And this traffic on this set of channels is, of course, what we would want to intercept if, in fact, we wanted to listen to the phone call. So you appreciate that this is basically a multi-frequency problem with a moving, unpredictable target. Since the information where you would have to look already comes encrypted, right? These frequencies also are spread widely across the available GSM band, so they're not at all adjacent to each other and basically easy to sniff as a package. GSM-900, the T-Mobile and Vodafone allocated band in Germany, they use 35 megahertz of spectrum for each downlink and uplink, which is broken into packets for those two operators. And then each operator takes some subset of what they got allocated to a cell, typically spread across the spectrum for the set noise resistance. And then each phone call, again, gets a subset of the base station's allocation. And again, as widely spread as possible for noise resistance. So the signal processing or the signal capturing challenge is to capture diverse frequencies into 35 megahertz chunks of spectrum, right? And this channel has been solved a long time ago by intelligence and law enforcement suppliers. And starting on the right side of this slide, what they're using are custom, fairly expensive boards with big FPGAs and very fast AD converters. They can actually record and process an entire GSM band at once. Those devices come at 40, 50,000 euros, so they're certainly not a reachable research tool for us. However, the same idea has been shrunk to more affordable and more open hardware, programmable radios, USRP being one example. Those two use FPGAs and AD converters, both not quite as big as these commercial boards, to just suck down a configurable chunk of spectrum. With 4 of these USRP2s, you can again capture all of GSM 900. Right? We're talking something like 5,000 euros for those. The USRP1s are more limited in the amount of bandwidth they can transmit due to the USB interface. Some of you may already have them though, so they're certainly a useful GSM tool, and again, a little cheaper. I'm making a huge jump, again, in the limitation of frequency, but also in the price, come ordinary phones. Every phone should have the capability of recording GSM data, right? That's what they're built for. So taking a 10 euro phone, which is what these are, somebody should be able to reprogram it in such a way to act as a let's call it a debugging device for GSM, right? And that's what the Osmocom team, and among them Sylvain, did over the past year or so. And I'll let him explain all the loops he had to jump through to actually create a 10 euro GSM debugger.
Yeah. We started with those cheap phones, and at the start of last year, Harald and Dieter started writing open source baseband firmware for those phones, which implemented all the normal phone functions. So it could act as a real phone. Receiving raw GSM data is not part of a normal phone function. There is one main thing that gets in the way, and it's the DSP, because basically, the GSM will transmit packets of information in bursts, and the first step of layer 1, things like encryption, forward error correction, and things like that, will be handled by the DSP itself, and then the DSP will give to the ARM core of the phone a reconstructed layer 2 packet. This is bad for us for sniffing, because we really want the raw burst output, because this is what Kraken wants, and so to debug we need this. So the first step was to patch the DSP. The DSP is ROM based, but you can patch some function in RAM, and that's what took most of the time, is to extract the raw burst data and basically disable all the higher level logic, forward error correction and things like that, and just get the DSP to give us exactly what it took from the air. It's not the raw IQ data, it's the demodulated bits. So we don't have to do the demodulation, and we enjoy the very good demodulation algorithm that TI wrote for their phones. So with this, we can capture one time slot of each GSM frame, because this is what a phone usually does. It only listens to its time slot. With a little more patching, you can actually get it to capture more than that. Currently up to 4, but you could go up to 6. There is 8 time slot in one frame, by the way. But the problem you encounter then is to get the data off the phone, because you only have the serial port, and you need to, with some special tricks and the non-standard baud rate, I'll skip the detail, but basically you need a faster USB cable to get all the data to the PC for processing. And when we've done this, we can get much more data. And one nice thing about the phone is that it can switch frequency very fast because it needs that to follow. It's a normal phone function to follow hopping, which means we can even retune between the uplink and the downlink, so we can, with a single phone, capture both what the BTS sends to the phone and what the phone sends to the BTS, because they're slightly shifted in time, so we can retune between both. To do that, however, there is one additional step. If you're not very close to your target, like 20 meters or so, the phone has a filter that will try to reduce noise and only sends the good frequency to the radio in the phone. If you want to capture uplink, which is in a different frequency band, you need to remove that filter. And with this, you'll get like 100, 200 meters or so uplink listening range. So this is what I'm going to demonstrate now.
Exactly. Can we switch over to the other computer once again?
Okay.
Thank you.
Okay. So here I'm using 4 of these phones connected to 4 serial ports on my PC. I just need to start everything. And okay, so I started all the phones. Okay, the phones are started, and here I have another application where I tell him to listen to ARFkin 671. This is the cell, the only cell you get here for this provider. Okay, 4 phones, and here I introduce the TIMZ of my target. So I tell him, as soon as you see a conversation, some messages that are not for my target phone, you just drop them. I don't need them. I only want my target.
Mm-hmm. To emphasize this for any law enforcement or lawyer in the room. So we are sniffing on a live network, one of the commercial operators in Germany, but we're only sniffing data that's specifically sent to this very phone, since we found out its identity before. We wouldn't need to apply this filter, but to stay on the right side of the law, kind of wanted to.
Okay, so now the phone is just looking at every channel that's being assigned, and if it's not for my phone, it just drops the data. Now I'm just gonna send a new text message to this phone. If I find this phone number. Okay. So here at some point I should see a text message. Okay, so this was it. Okay, I'm gonna stop the capture now and try to show it. If I can find it back. Okay, here I recognize it because I see the ciphering mode command, which is the order from the network to switch to ciphered mode. If it was not my SMS, I would have dropped the conversation before I even get to there. And here I see the paging. Okay, the resolution sucks. And yeah, this paging response is for my TIMZ, so this was the SMS. Okay, if I look here, these are all the conversations that have been recorded. As you can see, most of them are very, very small because there is only one packet, the packet that says if it was for this phone or not, except this one, which is bigger because it basically recorded the entire SMS. And that's it for now, I think.
Mm-hmm.
Yeah.
Pushing back once again, please. Can we switch the display again? Thank you. So this is how we recorded data and displayed the data up until the point where it says, now please start encryption. So the logical next step is to crack that encryption, right? Again, tiny bit of background. The phone SIM card and the home operator share a secret key. That key is used for billing purposes and all of this, so it's really well protected since it protects the monetary streams of the operators. If you know that key, you basically make calls on somebody else's account. There's another key that's much less well protected, since it only protects your private data. That's the... That's the session key. And the session key is derived from this master key in the SIM card and shared with the phone, and it's derived in the backend system and shared with the base station. So now the phone and the base station have a secret key, a session key, that they can use to encrypt text messages, phone calls, and what have you. The name session key should suggest that this key is only used once for one session, but in fact it's recycled a couple of times, and then a new key is generated. We'll use this property in the next demo, because we'll crack a key now, show each step, do the slow way, and use that key to crack the next data. I'm just going to go over this very briefly, since basically we discussed this a year ago here. The fact that the A51 keys are vulnerable to pre-computation attacks. We did release a set of rainbow tables a year ago that would allow a computer with this set of 2 terabytes in tables to crack keys in a couple of seconds. We have since improved the approach a little bit, well, actually significant, but with small steps, and computed a second rainbow table set. It's again 2 terabytes in size, but it's much lighter on the computational load. So a normal computer with just a CPU and maybe 4 or 5 hard disks can now crack keys. And how fast is yours? 20 seconds, roughly?
Here, yeah. But
yeah. So yet another component of the debugging tool set. For details, refer to last year's talk. The second table set has been put on BitTorrent, again, the faster one. But back to the data we just captured. What part of the data we're going to look at now? Well, certainly we're not going to look at the encrypted part, which the non-encrypted part, which we already displayed. The next packets, though, that weren't displayed in Wireshark since they couldn't be processed, were still recorded onto the hard disk in the encrypted version. And what's being encrypted in GSM is not the packet itself, but rather a transposition of that packet onto a larger number of bits for error resistance that chopped down in 4 bursts. So the quantity of data we work with when cracking keys is a burst. For all practical purposes, it doesn't really matter what we work with, since we're only interested in the encryption part of this message. In fact, what we need to do is predict what one of these bursts would be, right? And then see what's being transmitted over the air, and derive from those 2, the one guess and the one observation, what the encryption did. The encryption is simply an XOR.